Now that we've solved for the ideal gas contribution to our delta H, what we need to solve for now is the non-ideal gas contribution, that H departure function. All right, so to calculate our HI departure, what we need to use is the equation of state that we're assuming. So in our case, our model equation of state is going to be the van der Waals gas equation of state. Right? And so we have, for the van der Waals gas, we have pressure is equal to RT V minus B minus A molar volume V squared. Okay? All right, and so when we have the departure function, well, even before I go there, in the van der Waals gas equation of state, our A is not 0 and our B is not 0. And so, in the original form of the departure function that I wrote out, what you want to do there is you wanted to take the partial derivative of your equation of state, the dV dt at constant p. But in our case, with our equation of state, we can't really solve for it explicitly for volume. We can't just get volume on the left-hand side and then all the other parameters on the right, just based on the functional form of this equation. All right, and so can't solve for V explicitly. And so when we calculate our departure function, the form we want to use is the dV form. Okay? All right, and what I mean by that is our HI departure function is going to be equal to RT ZI minus 1 plus the integral of V going to infinity to VI. That integral, and what the integrand is this. Okay? And the reason this form is more useful when we're dealing with the van der Waals equation of state is because now the partial derivative we need to take is dP dt. And so our equation's solved explicitly for pressure already. So that helps simplify the derivative. And then, after we figure out what our integrand is, we would just integrate with respect to volume. All right, and so for our departure function, to calculate it, we need to use this dP dt, or we need to figure out what dP dt is. And so in the van der Waals equation of state, only the first term has a temperature, the second term does not. So when we take the derivative, we just end up with R V minus B. And that's all it is. Okay, so as we go through the departure function, we have Zi minus 1 plus the integral of t times that partial derivative, so R V minus B minus, and now we plug in for pressure, which is, we just take this equation and jam it in here. So RT VB, that's A squared. Okay, this term and this term cancel. The negative sign turns that positive. And so what we're left with is RT ZI minus 1 plus the integral of infinity to VI A over V squared dV. And so this integral, RT ZI minus 1 minus, in the end, 1 over vi, whatever your vi is, minus 1 over infinity. Okay? So we have a 1 over infinity here. That's the same. And 1 over infinity is just 0. And I want to remind you that this z factor here, this is the compressibility factor. This is just pi vi over r ti, from that virial equation of state. Okay, in any case, so for a departure function, for the van der Waals equation of state, it simplifies down to this. Okay. All right, so now that we have a functional form for the departure function, let's attempt to actually plug in some values. But there is, at least another roadblock that we need to overcome. So if I write out the departure function for stream 1, and I write out the departure function, or the compressibility factor for stream 1, we see in order to calculate these things, we need volume. Okay? But we weren't given volume, right? What we're given are pressures and temperatures. And so if we take a look at the van der Waals equation of state again, as I mentioned earlier, we can't solve this explicitly for volume. All right? And so but we need that volume term to calculate our departure function and our compressibility factor. And so in order to get the volume, since we do know pressure and temperature and all these other things are constants, what we could do is just solve for it implicitly. All right, and so we'll use to do this, we'll use the approach that you learned about in your computations class, where you just define an objective function, where you just rearrange your equation implicitly, and then you apply your numerical method that finds the value of v1 that makes your objective function equal to 0. Okay? All right, so essentially, you can use whatever method you want to do this. So for example, you could use Newton's method. But essentially what you're doing is you're trying to find the root of your objective function. Okay? And of course, both Excel and MATLAB have built-in functions that can do this for you as well. And so it's fine to use those functions for these calculations. In any case, if you went out and did the root finding for the inlet stream, you would find that V1 is equal to 4.986 e to the negative 3 meters cubed per mole. So once we have V1, we could find Z1 That's 0.9995. So that tells us we're pretty close to ideal, though, but not perfectly ideal. So we found Z1. We could also find H1 departure, which once again is just RT, Z1 minus, there's also T1, minus A over V1. And for that, we get a value of negative 48.7 joules per mole. Okay, so that's how we solve for the departure function for H1. find it for H2, it's the same exact approach. H2 departure. Root find in order to find V2. You can see the value now is a bit larger than V1. Find Z2, 0.998. So you can see we're getting further away from 1. And so that means we're becoming more non-ideal. Okay? And then H2 departure would be negative 20.5 joules per mole. Okay? Alright, so now that we've solved for both the ideal gas and the departure function contributions to the total delta H, from our energy balance, we could relate those things back to the normalized shaft work. Plus H2 departure minus H1. Okay. Alright, and so what we're taking is the ideal gas contribution. And then we're taking the values for each of our departure functions. Minus negative 48.7 joule per mole. And what we find is that the shaft work is just equal to 9261 joules per mole. Right, and so what I could point out here is that if we compare this value to our ideal gas value, with the ideal gas value we would expect to get, slightly, a little bit more work out of the methane gas. But due to these non-idealities, this tells us that the work we would expect to get per mole of methane we feed in is slightly less as far as the magnitude is concerned.